In this final video looking at the off-grid telecommunications site, we're going to redo the entire project using the Virtual Energy Analyzer. So the Virtual Energy Analyzer will provide us with default values for this project. We will specify what type of project it is, where it's located, and rather than then starting with a blank analysis, we'll start with an analysis that has what we hope are appropriate default values. We'll have to inspect those values to see how similar they are and how appropriate they are to our existing project. The costs that the Virtual Energy Analyzer provides will be selected to be appropriate for North America, and this project being done in Ecuador may have significantly different costs, and we may see significant differences between the costs I assumed when I did the analysis up till this point and those provided by the Virtual Energy Analyzer. Furthermore, we've done our analysis in US dollars, but when RedScreen's Virtual Energy Analyzer provides costs, it provides it in Canadian dollars. So we will have to do it in Canadian dollars. And just to put these numbers in context, at the time of recording, there's about $1.35 Canadian per US dollar. I'm going to go first to the File Settings page here, and I'm going to ensure that before I launch the Virtual Energy Analyzer, for the default setting for the heating value reference, I select the lower heating value. That way, when it launches, it'll use the same convention for the energy contained in fuel as I've used for the current analysis. However, I'm going to leave this currency at dollars, which will refer to Canadian dollars, and we can see that when it launches, there's no conversion rate between Canadian and US dollars. Even if I put in a conversion rate here and I launch it, the Virtual Energy Analyzer is not going to change the cost from Canadian dollars. So that would be a problem, because it's, if we selected US dollars and put in a conversion rate here, the Virtual Energy Analyzer will show us values in US dollars, but they'll be the monetary value in Canadian dollars, and it will ignore this conversion rate. So we don't want to do that, so we're going to have to do this in Canadian dollars. So now I go to the home page and I launch the Virtual Energy Analyzer here. And it recognizes that our current project is a power storage off-grid project, so I'm currently selected the right thing there. Similarly, it's a photovoltaic project, so I select that. But for the description, I have to choose for the type of base case and proposed case project and the load. The first option is going from a genset to a photovoltaic plus battery system. So that's actually what we want. And there's an option here for 24 kilowatt hours per day, which is very close to the 25 kilowatt hours per day that we're using. So let's do that. And I don't need to change the location. It'll get reused here. I might want to zoom in a bit so the map that is saved to the location page shows us the general area here. I hit calculate and RedScreen fills out the analysis with these default values. So there we are here on the location page. We see we have the appropriate climate data. When we go to the facility page, everything's been filled out here, so that's good. Now when we go to the energy page, the first thing we have to see is that some of these values are appropriate for North America, but don't reflect our project in Ecuador. So the first of these is the diesel price here at $1.20 Canadian. So you might recall our diesel price for Ecuador was 60 US cents, which would work out to about 80 Canadian cents per liter. So the price here is 50% higher. I'm just going to leave that alone and look at the analysis as it's provided by RedScreen, and just note values that you would have to pay attention to if you were doing this analysis. The next thing I will do is I will go to the power system and load characteristics and look at the base case and the load that's being specified. So it's configured this with a reciprocating engine running on diesel. Wonderful. There's the $1.20 per liter. We know that's not appropriate for this project. It's selected a capacity of 5.5 kilowatts. It's a bit smaller than our 7 kilowatts, but that's fine. Here's the first really major difference. The heat rate here is 21,280 kilojoules per kilowatt hour. And you might recall, and I'm going to show you the analysis we just did, going back to the energy page here, you might recall that we used, based on the help, 12,000 kilojoules per kilowatt hour. So this is a major difference, and you might ask yourself, well, why is that so different? And I would argue actually that the default provided by RETScreen is more appropriate than the value I took from the help here. So I blindly used help to pick 12,000, but 12,000 kilojoules per kilowatt hour assumes that the genset is operating at or near its rated capacity of 5.5 or 7 kilowatts. And that's clearly not going to be the case because we have 25 kilowatt hours of load, or 24 in this case, and a 5.5 or 7 kilowatt genset. So most of the time it's going to be operating at a very low loading level. This will have consequences for lifetime, but also efficiency. And the efficiency consequences should show up here in a much higher heat rate. That is, it's going to require many more kilojoules of fuel energy to provide a kilowatt hour of electricity if it's operating inefficiently. So this value here is probably closer to reality than the 12,000 we picked. The annual O&M costs are 3,000. That's much higher than what we assumed here at 1,000. But it makes sense that it would be more expensive to perform annual O&M in a corporate setting in Canada than in Ecuador, quite possibly. The load here is 24. We have 25. It's picked 0 intermittent resource correlation, so we're very close there. And the load is reflected in the annual AC. It's picked entirely AC load by default, so that works for us as well. And the peak load, it's assumed, is 5 kilowatts, which happens to be the peak load that we've assumed as well. Next, we can move on to the inverter and battery page here, and the inverter and battery page here as well. And we see right here at the bottom that there's a bunch of notes discussing the assumptions made in the archetype. And you could read those over to understand what it's presenting, but I'm just going to look at the values here. In our system, the analysis we did, we assumed that there was a 5 kilowatt inverter with an efficiency of 93% that we were going to pay about $1,500 for. Here, it's also picked a 5 kilowatt inverter, but the efficiency is only 85%, so it's assumed it's a less efficient unit, possibly because it's an inverter charger operating at low loading level, and it's not included the initial costs. That was a point we discussed when we did our analysis, whether these should be included here or whether we should just assume, as on the indicated in the cost database for the PV system, that they're wrapped into the cost of the PV system. We included them. They don't in the virtual energy analyzer defaults or the archetype. Looking at the battery here, we chose 2 days of autonomy and ended up with a 72 kilowatt hour battery. This was based on a maximum depth of discharge of 80%. They have chosen 1.5 days of autonomy, so less autonomy, but they've limited the depth of discharge to 50%. And as a consequence, they've ended up with a significantly larger battery, 91.2 kilowatt hours. Also, the battery is more costly, $319 versus $259, although actually that works out to pretty much the same price in Canadian dollars. So $29,000 for the battery here in the virtual energy analyzer analysis, and $18,700 US dollars here. So multiplying that by 1.35 to do the currency conversion, we end up with about $26,000 Canadian. So not radically different from what is provided here. Now, one thing you might notice is the selection here of a minimum battery temperature as the temperature control method and -10. And that might look a bit surprising to you. You might recall we used ambient, Minimum battery temperature, if you look on the help here, simply means it's going to establish a floor temperature. And it's going to assume that there is some mechanism that prevents the battery temperature from going below this specified minimum battery temperature. It's just establishing a floor. When the mechanism is not activated because the battery would be colder than -10, the assumption is the same, that it's going to follow the ambient air temperature. So because our site climate data never attains temperatures that low, this makes no difference. And we see that the average battery temperature derating of 6.3% here is essentially the same as the average battery temperature derating of 6% that was in our analysis. So don't let this -10 throw you. It's just saying the battery's never going to go below -10. There's some mechanism in place there, but at this site that mechanism would never activate because the site is quite warm. Going on to the photovoltaic system, we see it's oriented it towards the north because we're at the equator, so that's good. It's picked a higher slope angle, so it's slightly more sloped. As a consequence, it's going to get a little tiny bit less solar energy in the plane of the array, right? We got 4.38 with our choice. They got 4.30 with the virtual energy analyzer. Not a big difference. We can see that it's very nearly achieving 100% of the load, but not quite. So we might have to adjust, for instance, the sizing of the PV system or the days of autonomy for the battery if we really want to achieve 100% here. But we can see, comparing the values here, that it's picked an 11.48 kilowatt photovoltaic array, and we've picked 12 kilowatts. So very similar sizing there. The reason that it doesn't achieve the full load here, there are two reasons. First, certain choices, for instance, like the battery efficiency and the inverter efficiency, are different between the virtual energy analyzer and the analysis we did. But more important, the miscellaneous losses that the virtual energy analyzer has picked at 15% are higher than our 10% miscellaneous losses. Here again we see much higher costs, at least for the initial costs, $30,000 for the array versus 26,000 Canadian dollars, converting to Canadian dollars here. 15% higher, but remember there's that conversion in price there. In terms of the O&M costs, they're very similar. Going to the cost page, this will be interesting because we'll see whether it's included the same replacement costs as us. So looking at the initial costs here for the virtual energy analyzer, we see that there's those initial costs for the baseload photovoltaic system and the battery, and it's put in a credit of $10,000 for the purchase of the diesel-fired genset in the base case. We have that same credit here. Here's this cost correction. Let's take that out so we can compare our original analysis with the virtual energy analyzer. So overall, the incremental initial costs are 49,000 or 50,000 Canadian dollars according to the virtual energy analyzer, and 30,000 US dollars according to our analysis. And that works out to about 40,000 US dollars. So there's 25% higher according to the virtual energy analyzer. Let's look here at the periodic costs and the annual O&M and fuel costs. And here we see the annual O&M very similar. It's the fuel costs that are really quite different here. And that's for three reasons. First, we're consuming more fuel because we're assuming a less efficient genset. That's reflected in the quantity of fuel consumed. Second, this number, the cost of fuel, incorporates two components that are higher according to the virtual energy analyzer. One component is simply the cost of diesel fuel. That's higher. The second is the annual O&M maintenance for the diesel generator. That's also higher. So this unit cost is significantly higher here. And that's why we end up with a much higher fuel cost in the base case. Now looking at the periodic costs, it has generator replacement every 2 years for $10,000. we have generator replacement or overhaul every 3 years for $6,000 US. We have the proposed case battery replacement at 10 years here. The virtual energy analyzer has it every 6 years and a much more expensive battery. And then proposed case inverter replacement every 13 years. That's very similar in the two. On the emissions page, we see that it has calculated 13.1 tons of CO2 emissions reductions. We have calculated 7.7. That stems directly from the assumption that the diesel-powered generator is much less efficient. And I think that's actually a better assumption. So this is probably a better first estimate of the emissions due to the base case than what we assumed. And finally, going to the finance page here, we can return to a level 1 analysis and configure it to have 0 debt, 2.5% inflation, and 25 years. And then we can compare that with the finance page from this project. And we can see there's definitely a similarity in the form of the curves. This one from the virtual energy analyzer has less jagged changes, and it looks more positive at 23.8% pre-tax IRR on equity, on assets rather, versus 12.3% in our original analysis before the cost correction. The simple payback, 11.8 years, is much longer in our project, and the equity payback is much longer as well. But there are strong similarities in the project, and now it would be for us to go back and change mainly the costs to make them reflect the situation in Ecuador, or we could go back to our original analysis and re-examine some of our assumptions. And perhaps the assumption that I would most want to re-examine there is our assumption about the efficiency of the genset. I think we were being terribly optimistic by using that value from the help. I think we should assume a less efficient genset because it's operating at such a low loading level. All right, that's it for this off-grid telecommunications site. In the next series of videos, we're going to look at a different type of system. We'll look at village electrification, where in the base case we would extend the grid to the village, and in the proposed case we will use a photovoltaics plus battery plus diesel-fired genset system.